In this video, we're going to discuss the cross product of two vectors. So the way we're going to write the cross product, let's say we want the cross product of vectors u and v. We're going to write vector u. We use an x for the cross product symbol. So vector u crossed with vector v is written like this. The cross product is defined for two vectors that are in R3. So we don't talk about the cross product in R2 or R4 or any other dimension. It's just specific to 3 dimensions. So let's see a first example of how we calculate the cross product. Let's say vector u is 1, 2, 1, and let's say vector v is 3, negative 1, 4. The way we're going to calculate the cross product is we're going to write out the components of vector u, and we're going to recopy the first 2 components. So we go 1, 2, 1, and then we recopy the 1, 2. Underneath that, we're going to do the same thing for v. So here's us writing out the components of v, and then just recopy the first 2 components. First of all, we're going to ignore the first column here because that's just a placeholder. We're going to move into column 2. The operation we're going to do, calculate a forwards product minus a backwards product. So we're going to go 2 times 4 minus 1 times negative 1. So this is actually creating the first component of the cross product. So we're just thinking of this X pattern where we go forwards product minus backwards product, and that's creating this number here. And we're going to do that all the way across. So we're going to calculate forwards product minus backwards product. That's going to create this number here. And then forwards product minus backwards product, that's going to create this number here. So what we're saying is that the cross product of 2 vectors then is going to be a vector in R3. It's going to have 3 components, and each of these 3 components is coming from this process of taking the forwards product minus the backwards product. So for this particular example, u cross v, if we did all the algebra, it would look like 9 minus 1 minus 7. So let's try an example where we work through all the details. So same vectors u and v as we had before, and what we're going to do in part A is we're going to compute the cross product of v with u. Okay, so we write out our components of our first vector, v, copy out the first 2 components of that vector again, and then underneath that do the same thing for the second vector. So the second vector in our cross product here is this vector u. We're going to write 1, 2, 1, and we're just going to recopy the first 2 components. So we ignore the first column, that's just a placeholder. We start with the second column, and we're doing this calculation of forwards product minus backwards product. So we'd go negative 1 minus 8 is negative 9. Okay, and these numbers that we're creating are building the vector v cross u. So v cross u is negative 9, and it's going to have 2 other components. All right, so to get the second component, we're going to go this product minus that product. So 4 minus 3 is 1. And then for the third component, 6 minus negative 1 is 7. So there we have v cross u. Now on the side here, just for reference, I'm going to write the cross product u cross v that we calculated in our first example. We found that to be 9, negative 1, negative 7. So already we might be observing something interesting that, it seems like when we do the cross product in the other order, we just get the negative of the original cross product. So we'll talk about that a bit more in a minute. Second computation that we're going to do here, we're going to see what happens if we take the vector u cross v and we do the dot product with u. Let's try that. So as we figured out in our first example, u cross v was the vector 9, negative 1, negative 7, and we're going to do the dot product with the vector u that we started with. So that was 1, 2, 1. Okay, so thinking back to the dot product, we multiply the first components together. So we get 9 times 1, plus we're multiplying the second components together. So negative 1 times 2, and then plus multiplying the third components together. So negative 7 times 1. Okay, and I don't really need these plus signs before the negative terms. So adding that up, we get 9 minus 2 minus 7 gives us 0. So it looks like when we take the dot product of a cross product with one of the vectors involved, we get 0. And in fact, that's going to be true in general as well. So let's write down a couple of facts to encode some of the observations that we've made here. So a couple of facts about the cross product. If you do the cross product of V with U, so V cross U, it's going to be exactly the negative of U cross V. So order matters when you're doing the cross product. Second fact, the cross product, U cross V, is orthogonal to both vectors U and V. But geometrically, what this is saying is that if you've got two vectors, U and V, positioned like this, then your cross product is going to be perpendicular to these two vectors. So if you think about U and V as lying in a plane, that tells you that your cross product is either going to be pointing up out of that plane, straight up out of that plane, or straight down below that plane. So for now, we'll just draw the picture like this, and we'll say U cross V is pointing down like that, perpendicular to both of these two vectors here. So just to rephrase our previous geometry fact, we could say the cross product U cross V is a normal for the plane containing U and V. So let's redraw sort of a similar picture to what we had a minute ago. So let's say now vector U is sitting over here, vector V is sitting here. U and V then define this plane. And when we calculate the cross product, U cross V, what we're getting is something that's perpendicular to that entire plane. So U cross V is a normal for the plane. It gives us a quick way of finding a normal vector to that plane. And then we should talk about the direction of U cross V. So in this picture, U cross V is pointing up out of the plane. And the way that we know that for sure is by something called the right-hand rule. So if you're trying to decide whether U cross V is pointing up or down in this picture, it's the right-hand rule that determines that. So let's talk about the right-hand rule in a bit more detail. So here's a demonstration of the right-hand rule. We're going to use our right hand, and we're going to keep our right hand flat and just keep it lined up with the first vector. And then we're going to let our fingers curl towards the second vector. And as that happens, that's going to gently pull our thumb either up or down. So in this case, if we were calculating the cross product of A cross B, that would be pointing upwards. That's what our thumb is telling us. So here's a new picture. Vector A crossed with vector B. A cross B is going to be pointing up out of this plane. But suppose now we had our vectors in a different orientation. So again, I'm going to use my right hand, keeping my right hand flat. I want to line my right hand up with vector A. So I could try doing it like this, but my fingers do not want to curl backwards. So what I can do is I can think of positioning my hand this way. So I've just rotated my wrist. So lining my hand up flat with vector A, letting my fingers curl towards B. Which way is my thumb pointing? Well, down. My thumb's pointing down. So A cross B is going to be pointing down. If you imagine A and B lying on this plane, A cross B is pointing down below this piece of paper. Let's find the general form of the plane through 3 given points. So the idea is that we've got these 3 points in 3D, and if we can form a couple of vectors out of those 3 points, then we can visualize the plane that's containing those points. And in order to get the general form, we would be really interested in finding a normal vector to this plane. So let's put some specifics on here. Let's say this is point A, and that's point B, that's point C. So we could calculate the vectors AB and AC. And then once we had those, then we can calculate the normal vector. Let's label that in our picture as well. We could calculate a normal vector using the cross product. So let's say N is going to be AB crossed with AC. Now, if we're really paying attention to the right-hand rule, then in fact, in this diagram, it would probably be more appropriate to draw N pointing downwards so that we're obeying that geometry. However, this is just an abstract drawing. I haven't actually drawn A, B, and C carefully according to the coordinate axes. So if you do a careful sketch, you may well end up with a version where N is pointing upwards. In the end, the direction in the picture is not going to matter. It's not going to make an impact on our answer. So the point is we're finding this normal vector n, which is perpendicular to both AB and AC, and we're doing that using the cross product because that's what generates a vector that's perpendicular to both of your two starting vectors. All right, so let's run through the algebra. To get vector AB, we're just going to go b minus a, so that's going to give us 1, -2, -2. And to get vector AC, let's think c minus a, so that's 0, -4, and -1. So now we can calculate the cross product of these guys. Let's do that over on the side. So I'm going to write out the first vector's components and just recopy the first two components. Write out the second vector's components and then recopy the first two components. And then we're just doing this X pattern, just ignoring the first column because it's just a placeholder. Okay, and this is going to give us our normal vector n. So let's do our calculation. We'd have +2 minus 8 would give us -6. Working our way across here, we'd have 0 minus a -1 would give us a +1, and then a -4 minus a 0 would give us a -4. So that's our normal vector. And then once we've got that, if we're looking for the general form of the equation of this plane, we can start with normal form, where we go n dot x equals n dot p, where p here is just the vectorization of any point on the plane. So you could use point A, point B, point C. It doesn't matter which one you use, you're still going to create the same general form at the end of the day. So let's plug in. Here's our normal vector, dotting that with the vector x, which just contains our variables, x, y, z. And we're saying that's equal to our normal vector dotted with the vectorization of any of our points. So let's scroll up to our points here. I'll just choose A by default, but you could equally well choose B or C. So I'll plug 1, 3, 6 in there, and we'll just do our algebra. So on the left side, our dot product looks like -6x plus y minus 4z. And on the right side, we'll compute this dot product. So -6 plus 3 minus 24 gives us -27. Or you could do something like multiply through by a negative would be fine as well. So 6x minus y plus 4z equals 27 if you think that looks better. So let's recall from earlier in chapter 1 that when you take the dot product of u and v, what you get is the length of u times length of v times cos theta, where theta is the angle between your two vectors. So similarly, we can talk about how the cross product relates to the lengths and the angle between the two vectors. So the fact is that if you take the length of the cross product, what you get is the product of the lengths of u and v times the sine of the angle between the two vectors. So the caution I would make here is that when we write down u cross v, let's remember that that's a vector. So in order to create a numerical quantity, what we're doing is we're taking the length of that vector, and we're saying that length is the product of the lengths of u and v times sine of the angle between them. And so there's a nice kind of parallel between, we've got one formula that involves the dot product, another formula that involves the cross product, one involves the cosine of the angle between the vectors, and the other involves the sine of the angle between the two vectors. So let's see how this might be useful for us from a geometry point of view. Let's show that the area of the triangle in this picture is half the length of the cross product. Well, notice that this triangle here is not a right triangle. So first thing I would think about is just redrawing this picture. And let's think about the height of this triangle. Let's just call it h. So we create the height just by dropping a perpendicular to the base. And we can zoom in on this left side of this triangle. So we've now created a right triangle. What do we know here? Well, we knew this was vector v. So we could say the hypotenuse now in this picture is the length of v. And we also know this angle. That's what we're calling theta, because we're told in the picture theta is the angle between vectors u and v. In our red triangle on the right side here, we should be able to find the height in terms of the angle and the length of the hypotenuse. We would say, well, sine of theta is going to be h over the hypotenuse, so h over the length of v. Or if we rearrange this, we could say this mystery height here is going to be length of v times sine theta. Okay, so we've basically done a little bit of side work to find the height of this triangle. What we're trying to do is find the area of this big blue triangle here. So we could say area is going to be half the base times the height. And we know the base is the length of u. So we've got half the length of u times the length of v times sine theta. And then we could say, oh, wait a minute, this part here looks familiar because we just said that if you take the length of u times the length of v and multiply that by sine of the angle between the two vectors, what you're getting is the length of u cross v. So we could actually more easily express this as just half the length of the cross product. So somehow the length of the cross product is telling us something about the area of a triangle. Specifically, if you take half the length of the cross product, you're getting exactly the area of the triangle formed by u and v. So let's just look back at the question and confirm that we've answered it. So we were supposed to show that the area of the triangle is exactly half the length of the cross product, and yes, we have done that. So let's encode this with a fact in case we need this later. So if you want the area of a triangle formed by vectors u and v, you take half the length of the cross product. And if you want the area of the entire parallelogram, well, you would just double that. So you'd have the length of the cross product. And that would apply anytime you've got two vectors u and v in R3. So just to connect these two formulas with the picture, so we've got vectors u and v in R3 positioned however we like. We can either talk about the area of the triangle formed by these two vectors, or we can talk about the area of the full parallelogram that would be formed if you recopied u and v. So let's put this into practice by finding the area of the triangle determined by these two vectors. All right, so I'll just draw sort of a generic picture to imagine what's going on. Let's say we have these two vectors, u and v. They would form a triangle, not necessarily a right triangle, so that's really important. In fact, I might even distort this a bit more just to illustrate that. So all we need to do to calculate the area of the triangle is take half the length of the cross product. All right, so let's start by calculating u cross v. We'll write down our vector u, recopy the first two components, do the same thing for v underneath. We ignore the first column because that's just a placeholder, and we're going to do this process of forwards product minus backwards product. And we'll just write our answer over here. So u cross v is going to create a vector with three components. The components are going to be 24 minus 15, which is 9, 10 minus 6, which is 4, and then 3 minus 8, which is negative 5. Okay, now what we're after is the length of u cross v. So that's going to be the square root of 81 plus 16 plus 25, so which works out to root 122. So then we could say the area of the triangle is going to be 1/2 of the length of the cross product. So in other words, root 122 over 2. Now we want to work towards a second way of thinking about the cross product calculation. So to do that, we're going to do a couple of quick definitions here. We're going to introduce the idea of a matrix. So a matrix is just a rectangular array, usually containing numbers. And often we call matrices by capital letter names like capital A, capital B, etc. So for example, we could have this matrix capital A, which looks like this. So when we talk about a matrix, we often talk about the size of a matrix. And in specifying the size, we talk about how many rows by how many columns. So we always talk about rows first. For example, we'd look at this matrix here and we'd say, well, it's got 2 rows and 3 columns. So we would say matrix A is 2 by 3. Third definition that we need is the idea of the determinant of a matrix. And in notation, we can either write det A, or we can write A with vertical bars around it. So this sort of looks like an absolute value symbol, but in fact it's a determinant symbol. So the determinant is a number that's associated with a matrix. We'll see how to calculate this number in a moment. And it's only defined for square matrices. So when we say square matrices, we mean matrices that have the same number of rows as columns. So we can calculate the determinant of a 2 by 2 matrix or a 3 by 3 matrix, etc. So formulas for calculating the determinant of a matrix. We really need two formulas, one for a 2 by 2 matrix and one for a 3 by 3 matrix. So let's look at the easy situation first. If we want the determinant of the matrix ABCD, we usually write it like this. So if you're writing the determinant of a matrix, you don't need to write the vertical bars and then write the square brackets. It's just understood that if you write the vertical bars and then you write the entries of the matrix, that means calculate the determinant of this matrix. And look at this. This is actually encoding the forwards product minus the backwards product that we were talking about earlier. So you just go forwards product minus backwards product. That gives you your determinant. Now, for a 3 by 3 matrix, things get a little bit more complicated. So we're going to use this process called cofactor expansion to calculate the determinant of a 3 by 3 matrix. And the way it works is we're just going to circle the first row of the matrix, and we're going to work our way across this first row in the following way. So we're going to take the first number that we see in the matrix, A, and then we're going to cross out the row and the column that contain A, and that's just going to leave us with a little 2 by 2 matrix. We're going to multiply A by the determinant of that little 2 by 2 matrix. Okay, and then we're going to work our way across the top row in a similar way. We do have to be a little bit careful that there's a sign change on the second term, and we'll actually talk about that in a minute, why exactly there has to be a sign change. But we changed the sign of the middle term, so we're going to go minus B times. And then what are we doing? Well, we're going to cross out the row in the column that contains B. That's going to leave us with a little 2 by 2 matrix, D, F, G, I, and we're going to multiply the negative B times that little determinant. Okay, and then we're going to continue working our way across the top row. Then we're going to hit the number C, and we're going to go plus C times the little 2 by 2 determinant that results when we cross out the row and column containing C. So C is getting multiplied times this little 2 by 2 determinant that contains D, E, G, H. So just to summarize then this process of cofactor expansion, where we calculate the determinant of a 3 by 3 matrix, we work our way across the top row. You multiply each entry in the top row times the corresponding 2 by 2 determinant. And the only catch in doing this is that as you're summing these up, the second term gets a negative sign, which again, we'll talk about that in a minute. So let's do some practice with cofactor expansion. So we're going to compute the determinant of this 3 by 3 matrix using this process called cofactor expansion. So we are going to expand along the top row. We're going to have 1 times a certain 2 by 2 determinant minus 4 times a certain 2 by 2 determinant plus 6 times a certain 2 by 2 determinant. So the thing to be aware of at this point is that the second term always gets a sign change. Okay, and then once I had that structure written down, then I would start to think about, okay, specifically what numbers go into these 2 by 2 determinants. So looking at the first entry here, the 1, let's cross out the row and column containing the 1, and that leaves us with the 2 by 2 matrix 1, 3, 6, 7. Okay, so working our way across the top row then, we would get to the 4, and we would say let's cross out the row and column containing that 4. That's going to leave us with the little 2 by 2 matrix that looks like 2, 3, 0, 7. So we're going minus 4 times that 2 by 2 determinant. And then continuing to work our way across that top row, crossing out the row and column containing the 6. The 6 gets multiplied by the 2 by 2 determinant that looks like 2, 1, 0, 6. All right, and then in the next step, we can actually work out the values of these determinants. So we're going to go 1 times negative 11. Remember, every time you see a 2 by 2 determinant like this symbol just encodes this process of going forwards product minus backwards product. So then we're going to have minus 4 times, well, 14 minus 0 is 14. And then we go plus 6 times, well, 12 minus 0 is 12. Okay, so at the end of the day, we're getting a number. We've got minus 11 minus 56 plus 72 gives us 5 for the value of that determinant. Okay, so let's try a second calculation. We just need a little bit of practice to get comfortable with this process of cofactor expansion. So again, we're going to do a computation, and this time the determinant is just going to be written as the vertical bars. So here we go. We're going to work our way across the first row of this matrix, remembering that the second term gets a sign change. So it's going to be negative 1 times a certain 2 by 2 determinant, plus 4 times a certain 2 by 2 determinant, and then plus 6 times a certain 2 by 2 determinant. So again, I'm going to highlight the sign change. Okay, so starting with the negative 1, cross out the row and column containing the negative 1. That leaves us with this little 2 by 2 determinant. Doing the same thing across our matrix, now we're going to cross out the row and column for the negative 4. That also leaves us with this 2 by 2 determinant. And then finally crossing out the row and column containing the 6. We'll have this little 2 by 2 determinant. So cofactor expansion is really a way of taking a 3 by 3 determinant and reducing it into something involving 2 by 2 determinants. And then those 2 by 2 determinants can be calculated quickly. Because for a 2 by 2 determinant, we're just going forwards product minus backwards product. So we're getting negative 1 times 6 plus 4 times 6 plus 6 times 0. So overall, our determinant is 18. All right, well, the whole reason why we're talking about determinants is to take a new point of view on the cross product. So let's actually relate this back to the cross product. So to make a connection with the cross product, we need just a little bit of notation. We're going to let vector I represent the unit vector that just goes 1 unit along the x-axis, vector j, unit vector in the y direction, and vector k, unit vector in the z direction. So here's the second method for calculating the cross product. What we're going to do is consider this to be a 3 by 3 determinant. So what goes into the top row are just our vectors I, j, k. What goes into the middle row? The first vector, and what goes the second vector. All right, so let's just work through this example quickly. Expanding the 3 by 3 determinant in the usual way, you would expand along the top row here. So you'd say, okay, well, let's take vector I times this little 2 by 2 determinant, which would be negative 10. And then we go minus vector j, because there's always a sign change when you do your second term. So minus j times, well, we'd cross out the row and column containing the j, and that would give us 4 minus negative 18 would give us 22. Okay, and then continuing our cofactor expansion along the top row, we'd get to the k. We'd say k times this little 2 by 2 determinant, which would be 8 minus negative 6 would give us plus 14. So that's where the plus k times 14 comes from. Okay, so now we have this sort of strange looking expression here that involves vectors. And if we now write down what vector I is, well, it's the vector 1, 0, 0. If we write down what j is, it's 0, 1, 0. If we write down what k is, it's 0, 0, 1. Okay, so with a little bit of algebra, we can figure out that this is really representing a vector in 3D, which looks like negative 10, negative 22, 14. So this is another way of computing the cross product. So let's compute the cross product 1, 2, 1 with 3, negative 1, 4 using cofactor expansion. You may remember this is the exact example that we did at the beginning of the video when we first introduced the idea of the cross product. So now we're going to do that using our cofactor expansion method. Okay, so let's just call these vectors u and v. We'll say u cross v is equal to, well, it's going to be a 3 by 3 determinant. In the first row, we put our vectors I, j, k. In the second row, we fill in our first vector, and then we fill in the second vector below that. Okay, and then we're going to do our usual determinant calculation. So we're going to expand along the top row. So we're going to get vector I times a certain 2 by 2 determinant minus j times a certain 2 by 2 determinant plus k times a certain 2 by 2 determinant. And the thing to be a little careful of here is, remember, there's always that sign change on the second term. All right, so let's talk about crossing out the row and column containing the I. We'll just write down the little 2 by 2 determinant that results. And we'll do the same thing as we work our way across. So for the j term, just cross out that row and column. You'll have a little 2 by 2 determinant that looks like this. And then for the k term, cross out that row and column, and you'd have 1, 2, 3, -1 for your 2 by 2 determinant. All right, so let's calculate the details. Remember, every time we write down a 2 by 2 determinant, we're just talking about this forwards product minus backwards product. So that would be 9 minus j times 4 minus 3 is going to be 1. And then plus k times -1 minus 6 is going to be -7. Okay, so vector I represents the vector 1, 0, 0. So we're saying take 9 times that. And then vector j, instead of writing down vector j, let's remember that represents the vector 0, 1, 0. And then we're going to go -7 times k. Well, k is the vector 0, 0, 1. All right, so if we do a little bit of algebra then, if I really belabor the algebra, it would look like 9, 0, 0, and then plus 0, -1, 0, and then plus 0, 0, -7. And then we could add those together to create 9, -1, -7. But normally when we're working with vectors I, j, k, we actually usually just skip from this step to this step, because you can get used to the idea that whatever's being multiplied by the I just becomes your x component. So if you see 9i, that just represents the vector 9, 0, 0. Okay, so just looking at the coefficients of the ijk, we've got 9, we've got a -1, we've got a -7. So those become the components of our vector. And that's something that you're going to see often in many of your courses. So it's good to just be able to do that shortcut. Okay, so what we figured out at this point is that this new determinant calculation gives us a different way of thinking about the cross product. But what we haven't talked about yet is this sign change here. Our first way of doing the cross product, we said write out our first vector, recopy the first two components, do the same thing for the second vector, and then just ignore the first column because that's a placeholder, and you're doing this X pattern. Okay, so we now know this X pattern has a name. It's called calculating the determinant. So we calculate the determinant of these guys, and that gives us our first number. So when we calculate this second number here in the cross product, we're supposed to be looking at this determinant here. Now, if we look at what's happening with our cofactor expansion, so let's focus in on this term here in our cofactor expansion. Think about where that came from. When we were doing our determinant, we crossed out the row and column containing the j, and we wrote down the 2 by 2 determinant that looked like this. So, and this is essentially backwards. And if you reverse the columns in a determinant, what you get is actually a sign change. So the sign change here is correcting for the fact that you really have your columns backwards. So we're going to see 3 geometry formulas related to the cross product, and then we'll practice them. So first geometry formula we actually already saw. It says that if you have two vectors that are in R3, let's call them u and v, and you want to calculate the area of the parallelogram that's formed by these two vectors, then just take the length of the cross product. But we might say, well, what if we want to do the area of a parallelogram in R2? then we wouldn't be able to use the cross product because we don't have a cross product in R2. So instead, the formula becomes the absolute value of the determinant created by vectors u and v. So you just fill your two vectors into the rows of a matrix, and then you take the determinant of that matrix. And that makes sense because if u and v are in R2, then u has two components, v has two components. So that's creating a little square matrix. You can calculate the determinant of that matrix. The only caution here is that determinants can come out to negative numbers. So we have to take the absolute value of the determinant to be sure that that's really giving us an area. So this is why it was important to see the second method for calculating the cross product, because it was important for us to have the understanding that the cross product is somehow related to determinants. Okay, and then third geometry formula that we're going to practice, we want to talk about the volume of a parallelepiped in R3. Okay, so parallelepiped, that's just really a fancy way of saying a slanted box. So let's draw a picture. So imagine you have three vectors, u, v, and w, let's say, in R3. So you can think of these three vectors as forming a box. Just think about the fact that u and v create a parallelogram, which you could think of as the base of the box, and then w is coming in to give the box some height. So I might draw the full box here. So here's our parallelepiped or slanted box. It's sort of like a rectangular box, but the angles here do not have to be right angles. We can have u and v sitting at whatever angle we want. We can have this angle be whatever we want. So what I sort of visualize is, imagine you had a cardboard rectangular box, and then you just sort of kick it so that it starts slanting. That's basically a parallelepiped. So to get the volume of a parallelepiped in R3, we can also phrase this in terms of a determinant. It's going to be the absolute value of the determinant of the following 3x3 matrix. So imagine that u is a vector in R3. It's going to have three components. So we've got these three vectors, which each have three components. That creates a little 3x3 matrix. We can calculate the determinant, and then that determinant may be a negative number. So we need to be sure to take the absolute value of that determinant when we're talking about the volume of the parallelepiped. So we've got these three geometry formulas, and the common thread between them is that they all use the determinant in some way. Because while the first formula is phrased in terms of the cross product, we now know that the cross product is actually built out of little 2x2 determinants. So do these three vectors in R3 lie in a plane? Well, the answer will be yes, if and only if the volume of the parallelepiped is equal to 0. So let's think about this. Imagine that you have three vectors positioned in such a way that the plane formed by u and v is also the same plane that w lies in. So imagine these three guys somehow lie in a common plane. Then if you actually calculated the volume of the box that's formed by these three vectors, the volume would be 0 because essentially this box has no height. If you think about the base formed by just the vectors u and v, there's our base. How much height is w then giving us? Well, no height over that base. So the volume of the parallelepiped would be 0. So 0 volume corresponds to the vectors being in the same plane, whereas if you just chose three vectors randomly, the most likely scenario would be that u and v would be positioned like this. They would be defining some plane, and w would most likely be pointing either above or below this plane. So let's just draw w in our picture like this. Most likely scenarios that w does not belong to that plane, and then you can form a box which has a base that looks like this, and w would be giving us some height. So the volume of the box being non-zero corresponds to the situation where w is not in the same plane as u and v. So let's just put yes and no on here to just summarize this. So first scenario, the answer would be yes, the vectors do lie in a common plane. Volume is equal to 0. Second picture, no, the vectors do not all lie in a common plane and the volume is non-zero. So the question is just going to come down to calculating the volume of the parallelepiped. All right, so let's think volume of our parallelepiped, or you could say slanted box if you prefer. Volume of the slanted box is, well, it's the absolute value of a determinant. So it is important to have two different sets of vertical bars here. The small vertical bars represent absolute value. The large vertical bars represent the determinant. If you don't like that, you could say absolute value of the determinant of the following matrix, and that way you're less likely to get your vertical bars confused. Okay, now what we're going to do is just fill our vector u into the first row, v goes into the second row, and our vector w goes into the third row. So absolute value of this determinant is going to tell us the volume of the box. So we'll keep our absolute value sign on here until the end of the problem, and we'll just work on calculating the determinant by cofactor expansion. So it's going to be 1 times the following 2 by 2 determinant, 5, 9, negative 2, negative 3. Remember there's a sign change, so minus 4 times the 2 by 2 determinant that you get when you cross out that row and column. And then plus 7 times the following 2 by 2 determinant. So crossing out the row and column containing the 7, we'd have 2, 5, 1, negative 2. All right, so we're talking absolute value of the following. So 1 times minus 15 plus 18 is going to give us 3. Minus 4 times negative 6 minus 9 gives us negative 15. And then plus 7 times negative 4 minus 5 gives us negative 9. All right, so absolute value of, inside the absolute value, we've got 3 plus 60 minus 63, so that's 0, and absolute value of 0 is 0. So the volume of the parallelepiped is 0, and the answer to the question is yes. The 3 vectors do lie in a plane. So it is important to have the absolute value sign on here in general when you're calculating the volume of a parallelepiped, because a determinant can either come out positive, negative, or 0. And so if we're talking about a volume, certainly we want that volume to be non-negative. All right, let's find the area of the parallelogram determined by 2 vectors in R2. So the way I think about this is, well, I can form a 2 by 2 matrix just by putting these 2 vectors into the rows of that matrix. And then I can boil that down to a number just by taking the determinant, but a determinant may come out positive or negative. So if we're talking about area or volume, we need the absolute value. So the way we're going to get the area of this parallelogram is the absolute value of the determinant of this little matrix. So that's going to be the absolute value of, well, our determinant is 5 minus 18, so negative 13. In other words, absolute value of negative 13, 13. So the area of that parallelogram is 13. So in this video, we've seen 2 methods for calculating the cross product. We saw what I'll call the intuitive method first, and then we saw the method using cofactor expansion. And throughout the video, we've seen some nice geometry applications of what we can do with the cross product. Thanks for watching.